Hello. So in this new episode, we'll continue our discussion on the rationalizability and the dominated actions. Okay. So later we'll formally define the strictly dominated actions and weakly dominated actions. Right. So this is a continuation from our last episode where we discussed the rationalizable actions. Right. So recall that. So previously, we mentioned a lot of examples, right? So for example, in the prisoner's dilemma, okay. So the only the Nash equilibrium action confess was rationalizable, right? So in the prisoner's dilemma, okay, right. So only the Nash equilibrium action, which is confess, is rationalizable, right? Okay. However, in all the other games that we mentioned in this section of the strategic game, so both actions of those games for each player were both rationalizable, right? Okay, such as those pretty classical games that we mentioned several times, right, previously. So those games, if you recall that we have those both actions for each player, they're rationalizable, right? Both actions of each player are rationalizable. Okay. So the reason is because that in each case, both actions are used with positive probability in some mixed strategy Nash equilibrium, right? This is because in each case, both actions in those games of each player, both actions are used with some positive probabilities, right? In some mixed strategies. Mixed strategy Nash, right? Okay, so the rationalizability, so it puts no restriction on the outcomes in these games, right? And for many other games, the restrictions that the rationalizability imposes are pretty weak, right? But sometimes the restrictions from the rationalizability could give us some very precise answer. Okay, but we're not going to talk about those pretty special examples. Okay, but you can always refer to the textbook in the same chapter to see those other interesting examples. Okay. All right. So now let's continue on the next topic, which is also closely related to this concept. So, which is called the strictly dominated actions. Okay, and we're going to introduce a sort of an algorithm, which is called the very famous one, well-known one called the iterative elimination of strictly dominated actions. Right, so that's some algorithm that is often used for us to find the dominant or the actions which are not dominated. Right. Okay. So before that, let's first formally define those concepts. Okay. So an action of player I in a strategic game, it is a never best response if it is not a best response to any belief of player I. Okay. So an action of player I in a strategy game is a never best response if it's not a best response to any belief of player I. Okay, and this is a very straightforward definition, but we're not actually going to use that. Okay, so it's just a because there are some relevant propositions related to this, but we're not going to cover that. Okay, so this is just something that we know for now. And another definition for the strictly dominated action. Okay, so that is something that we're going to use extensively. So the action AI, okay, this looks like a pure, it's just an action, right, for player I. So we will also talk about the mixed strategy later. So action of player I in a strategy game with players, action profile, and utilities. So this is strictly dominated if there is a mixed strategy alpha I, okay, of player I such that the expected utility from this mixed strategy alpha I, so which we previously used this capital letter U, given all the other actions from minus I from other players and the mixed strategy player for player I, this has to be strictly greater than the utility, this is lowercase u, than the utility of player I, but so with the same a minus I and with some AI. Okay, so which is the action that we mentioned in the beginning of the definition, right? So and such that this is true for all a minus I, right? So and this part is very important. So this means that so for all a minus I, okay, right, yeah. So this part here, it means that so this is important because for all the other players, no matter what they're playing, what their actions are, the player I has a strictly higher expected utility using this mixed strategy. So if there exists this mixed strategy alpha I here, right? So it means that no matter what are the other players playing, given this mixed strategy alpha I here, if it exists, then this, and if it has a higher utility than some action AI, then in this case, this AI is always strictly dominated by some other actions, right? Okay. Right. So this AI here is strictly dominant in this case, and that's a very straightforward definition, right? Okay. So this where some notations were this UI, as we mentioned. This is A minus I and alpha I. So this is the payoff, okay, of player I if using the mixed strategy alpha I and other players' actions as A minus I, right? Okay. And in the textbook, we have some lemma. First, to To say that an action of a player in a finite strategic game is never best response if and only if it is strictly dominant. Okay, so we're not going to prove that, and that should be also straightforward, and you can refer to the textbook. But the more important result related to the strictly dominated actions, and also the algorithm called the iterative elimination of strictly dominated actions. So that would be the more important part. So before that, let's first define this algorithm and define what does it mean to survive the iterative elimination of that, right? Okay, so now let's do that. So definition. Okay. All right. Okay, let's do that. So the set X, which is a subset of A, action profile, of the outcomes of a finite strategic game, okay, N A I U I, okay, so this set of outcomes survives. So it's essentially saying this subset of some actions, right? Survives the iterated elimination of strictly dominated actions. Okay, so sometimes it's using those initial letters, right? I-E S-D-A, right? Iterated elimination of strictly dominated actions, but it's not necessary to just use those letters, right? So this would be confusing, but just use the formal definition for that. Okay, so if this X, okay, is the product of the xj's for all the j's here, and there exists a collection, okay, collection of what? Collection of xj's, but we're going to have some subscripts for the time, okay? So this time is to label the discrete time. For each time, we are going to eliminate some subset of the action from the action profile, right? So that we're what we're going to do. So here we need to label the time for this xj, right? So a collection. So this xj, we give some t here, and this t, and this j, of course, j is from n, and this t is from 0 to capital T. Okay, so this collection of sets that satisfies the following conditions for each j. Okay, so for what conditions? Let's have a look. Okay, all right, so the first is that xj, so for each j, xj0, if t is 0 for time at the initial time, so if xj0 is just the whole space aj, okay, and xjt, so the final xj would be the xj itself, okay. All right, so second, xj t plus 1 is a subset. It could be the same or a real subset of that xjt, okay, for each time step from 0 to t minus 1, okay. So it means that because we're going to eliminate some strictly dominated strategies, right? So at t plus 1, it has to be smaller, weakly smaller than the previous one, right? Okay, so the third, So for each time step from 0 all the way up to t minus 1, every action, okay, of player j in xjt, okay, excluding xjt plus 1. So this xjt excluding xjt plus 1, so this set essentially, so what's the meaning of that? That essentially means that something that is eliminated at this time step, right, is strictly dominated in the game and xit uit. So why do we have the superscript t here? So because we have different, at each time step we have a different game, okay? Because the game is defined by this tuple, right? And since the xj is changing all the time, right? So perhaps, right? So sometimes we're deleting some dominated strategies. So because this action space is changing all the time, so the game is actually changing. So the game is not the same all the time, right? So we need to use that notation to define a new game for each time step, right? So where uit for each I is the function ui restricted to the product of the xjets. Okay, so this looks like a x, two x's, but this is actually a product. So let's erase that. So this is a product over all the j's about the xjt. Okay. So for each time step, every action of player j in this deleted set, right? Deleted action set. So for every action in that set is strictly dominated in this game, in the time step t, where this uit for each I is the function ui restricted to this product, right? And this is because that it has to be so this we have to specify this utility function, right? So it cannot refer to something else because this is at time t, right? So it has to be restricted to the outcomes of the current time step. Okay. All right, not finished yet, right? So we have the last requirement. So no action in xjt, capital T here. So no action in xjt is strictly dominated in the final step, okay? So basically this definition illustrates, or it describes an algorithm for us to follow to how to show how to eliminate the strictly dominant actions, right? So at the final stage, at time t, capital T, so there's no action could be strictly dominated. Okay, so that ends this these algorithms. But actually, we can see from here that actually the a better way to describe an algorithm would be the pseudocode, right? So this mathematical definition for an algorithm is not very friendly, right? So that's something to be proved. Okay. All right, so now we have the definition, and then we could to begin our proposition to prove first to show that and later prove that the outcomes subset of the outcome survives this algorithm, the iterative elimination of the strictly dominant actions in this finite game. If that's true, then the set of outcome xj would be the rationalizable actions. Okay, and we want to show the equivalence of those, right? Okay. All right. So let's write down the proposition first. If x, okay, the notations are not very nice here, so those look pretty the same. But this capital X equals to the product over all the j's for the xj's. So this subset of the actions survives iterated elimination of strictly dominated actions in a finite strategic game and AI UI. Okay. All right. If that's true, then xj is the set of rationalizable actions, right? It's the set of i's rationalizable actions for each j. Okay. All right. Now let's prove that. Okay. Proof. Okay, so now let's first suppose that it's rationalizable. Okay. First part. Suppose AI is rationalizable. Okay. And what we are going to do is to make some set zj for all the j's, okay, be the profile of sets in a previous definition of the rationalizability. Okay. Okay, so you can refer to the previous definition for that. Okay, which supports AI. Okay. All right, so that AI would be the rationalizable, rationalizable. Okay, and then for any value of t, what we have is zj is a subset of xjt, and this is because each action in zj is a best response to some belief over the z minus j, and so it is not strictly dominated in the game at time t. Okay. Right, we have this since each action in zj is the best response to some belief. Okay. Over z minus j. And hence it is not strictly dominated in the game at time t. Okay. UI t. Okay. And actually here implicitly it uses some lemma which is proved previously in the textbook, and essentially says that saying that action of a player in a finite strategy game is never best response if and only if it's strictly dominated, right? But we're not going to prove that. So and you can refer to the textbook for that. Okay, it's not hard. So all right. So this AI is an element of Xi. Okay. So it is it survives if it is rationalizable. Okay. So now let's see the second part. So now what we're going to show is that for every j, every player j, so every member of xj, so if it survives, then it is each member of the survived set would be rationalizable. Okay, at each action. Okay, now to show for every j, every member or every element of xj is rationalizable. Okay, so that's the other direction. All right, so this would be if and only if, right? Okay, because we're proving both directions. Okay, so by the definition, so no action in xj is strictly dominated in the game, where the set of actions of each player I is xi. Okay. All right, let's write that down step by step. So by definition, no action in xj in the player j's survived set is strictly dominated, right? Okay. In which game? In the game where the set of actions of each player I is xi. Okay, in that game. So what? So by the same lemma that we mentioned, that we implicitly used previously. So by the lemma, so every action in xj is the best response among the members or among the elements of xj to some belief on x minus j. Okay, and that's also very straightforward. So every action in xj is the best response among the elements of xj to some belief. Okay, and it doesn't matter, just some belief that exists to some belief on x minus j. Okay, and what we need to show, okay, is that every action in xj is the best response among all the elements of the set ai to some belief on x minus j. Okay, so what we need to show that every action in xj is, and also later we'll give example of this algorithm, right? And we missed that previously. So action in xj is a best response among all the elements of aj to some belief on x minus j. Okay. Since we already have that, so by definition already have that, so no action in xj is strictly dominated in the game, right? Because it's survived, right? Where the set of actions of each player is xi. Okay, so every action in the survived set is a best response, right? Among some members of xj to some belief. Okay, and so what we need to show next is that every action in xj is a best response among all the members of the set aj. Okay, so previously we have it's true for elements of xj. Now we need to show that it's also true for the element of aj. Okay, then we could say that it's the survived one is also it's rationalizable, right? Because we have proved we will have proved it to be true for the whole space, right? Action space. Okay, so now let's do that. So if aj in xj is, so here we're using the proof by contradictions, right? So we're assuming something not true and to induce something, something to have some confliction, then the assumption will be false, right? So and then prove the thing that we need. So if aj in xj is not, okay, but actually this is not correct, right? If it is not a best response among all elements in aj, then what will happen is that there is a value of t such that, okay, aj is a best response. So it means that there will be some time step such that this aj is a best response among the elements of xj at time step t to some belief mu j on x minus j. Okay, that's standard. But it is not a best response among the elements of the previous time step. Okay, so essentially here it's essentially saying that if we're assuming something is false and later we'll induce some contradiction. So the false statement that we're assuming is that if this aj from xj, if it is not a best response among all the elements, if that's not best response among all the elements in the aj, okay, then there must exist some time step, okay, such that this is so it means that previously it was not, okay, but later it becomes a best response, okay. So implicitly it says that previously it was not best response, but it becomes a best response later, right? So that's essentially what we're talking about. So it becomes a best response later. So previously, so that's why we're saying that previously for t minus 1 time step, this is not AJ is not best response, but later at time step AJ, at time step T, this AJ becomes a best response, okay, to some belief. And we are not finished yet. So if that's the case, then this will happen, right? And further, okay, then there exists, then there is, same thing, an action, okay, which action? An action BJ, okay, BJ is what? BJ is the thing that is actually got eliminated in time t, right? From t minus 1 to t. So xj t minus 1 excluding xjt. So there must exist this eliminated action at this time step, right? That is a best response. So means that it was a best response, but it was also eliminated, right? But a best response should not be eliminated, right? That is the best response. So among the members or the elements, among the elements of xj t minus 1 to some belief, okay? All right. So there has to be this because AJ was not a best response previously, right? So it has to be some sort of a best response to the belief. But however, this BJ, this best response, got eliminated, right, during this time step change. Okay, and this is contradicting the fact that BJ got eliminated at T time step, right? So the contradiction is here, right? So it got eliminated at time T, and this B has to be a best response. This is because that this A, okay, this A was not a best response at T minus 1, right? And it becomes best response later. So that came from our false assumption where this AJ is not. This was a false assumption, right? Don't forget. So this proof is too long for a pretty simple concept. So for false, AJ was not best response for time t time step, and this was a false assumption. So by the contradiction, so the AJ should be a best response, right? And then we have completed this proof to show that for the survived set, it's also rationalizable, right? Okay, great. So that would be, and we still have an example left, right? Okay, so now let's do that. Okay, so we're using the figure on the textbook to show the intuition of the strictly dominated actions and the algorithm of this elimination, right? Okay, let's have player 1 to have top, middle, bottom actions. Player 2 could play left or right. So here, what we could get is 3 0 0 1 0 0 3 1 1 1 1 0. Okay. All right. And we could see from this game that, okay, so this action B for player 1 is strictly dominated by a mixed strategy. Okay. We should have some simpler example using the pure strategy to dominate the other one. But here we just use that example from the textbook. Okay. So basically the mix of T and B, the mix of T and M. Okay. So as we can see, the half of 3 and 0 would be 1.5, and the same here. So two 1.5s would be strictly greater than those two ones, right? Okay. So B is strictly dominated by a mix of T and M with half and half, right? So after that, so this is not a very good example, but we know what we're talking about, right? So this B just got eliminated. We just cross that out. Okay. So after we do that, then we consider we just take a look at this game again, right? So now we turn to player 2. So after B is done, B is removed, then what we could see is that this would be easier. So these two line, okay. So those ones are strictly greater than those zeros, right? Okay, so what we could tell from here is that L is strictly dominated. So be careful. This is dominated, not dominant, right? So dominated means that the one this L is worse, right? So L is dominated by R, right? So we just remove this column. Okay. Yeah, after we do that, then we just change maybe here to green, and we could see that M, so T here is strictly dominated by M, right? Because this 0 is strictly lower than this 3, so we just then cross out this T here. So the only outcome left is this M and R with 3 and 1, right? Okay, and after that, what we did is T is crossed out by M. Those are all strictly dominated, right? Not weakly by M. So MR is the only outcome surviving the algorithm. Okay, iterative elimination of strictly dominant actions. Okay, great. So lastly, let's have a look at the weakly dominated definition. Okay, but we're not going to have any example, but examples would be pretty similar, right? So it's just weak means that it involves the equality in the expression. Okay, we have the final definition, but we're not going to have example or any proposition of that. So action AI of player I in a strategic game, AI UI, okay. It is called weakly dominated if there exists a mixed strategy alpha I, okay, so of player I such that All right. So under the mixed strategies, given all the other players' actions and the mixed strategy for player I, this yields a weekly higher expected payoff for player I than the player I's payoff under pure strategy, AI, right? Okay, under the weekly dominant strategy. And this is true for, and very importantly, right, for all the other players' strategies, and this has to be true for all the players' strategies. And this UI, okay, A minus I, alpha I, is strictly greater than the UI, given all the other players' strategies. And this has to be true for at least for some actions from the other players, right? It can be weekly greater than all the other than the payoff for all the other players' actions, but there's no strictly higher one, right? There has to be something to be true here for some action for the other player. Where this UI is we just write it as the mixed payoff, right? Okay, we just know what it means. So basically, there's the payoff for player I if the player I uses the mixed strategy alpha I, and the other player's vector of actions, the profile of the actions with A minus I, right? Okay, so that's a brief definition for the weekly dominated actions in a strategic game, but we're not going to have any results for any other further results for that. So the main concept that we reviewed today would be discussed today would be just the strictly dominant strategies and the algorithm for the elimination of the iterated elimination of the weekly dominant actions, right? Because it's called iterated because we're doing this iteratively for those different players, right? We're doing this for player one, then player two, then player one, then player two, right? This alternatively, and until there's no strictly dominant strategy left, right? Okay, great.